So this talk is on directed hypercube routing, generalized Lehman-Ron theorem, and monotonicity testing. And this is a paper that is due to appear at ITCS 2025. This is joint work with my longtime collaborator, Deeparnab Chakrabarty, who's at Dartmouth. And I'm C. Seshadri, and I'll be presenting this talk. Before I proceed, I want to give thanks to people who've really influenced my academic career: Manindra Agarwal, Bernard Chazelle, Mike Sachs, Tammy Kolda, and Ali Pinar. And this specific result is actually dedicated to Dana Ron for her 60th birthday. And she has had a large influence on my academic career and on my work. And this paper is basically, comes from one of her very nice results. So let me begin by telling you what the Lehman-Ron theorem is. So let's consider the directed Boolean hypercube. So this is the graph or the structure where all the elements can be thought of as n bit strings or d bit strings. So I should say d is the dimension. Or you can also think of each element as a subset of a universe of d elements. Now we're going to think of this as a directed graph. So we're going to take basically the d-dimensional cube and direct the edges from lower Hamming weight to higher Hamming weight. Now what I've shown here are two pictures. On the left side, you have the sort of the dimensional picture as if it's, like a cube. And on the right side, you have what is called the level picture. So the level picture you can just think of as each oval is the set of all vertices whose Hamming weight is I. And so you have these level sets. Now, a very natural partial order that one can construct on the Boolean hypercube is just by containment, or the coordinate-wise partial order, and that's given by sort of the curly less than. So x is less than y if for all coordinates I, xi is less than equal to yi. You can also think of the Boolean hypercube as a collection of levels with regular bipartite graphs. So between every two levels, it's a regular bipartite graph because the degrees are all the same. And then you can see in this picture that from the ith level to the I plus first level, the degree from the I side to the I plus one side is exactly exactly d minus I. So this is the directed Boolean hypercube, sort of the object of our study. Now, by some basic facts is, by Hall's theorem, between two levels, because it's a regular bipartite graph, there is a perfect match. There is a matching from the smaller side to the larger side. And so what this leads to is actually something called the symmetric chain decomposition. You can actually decompose the Boolean hypercube into a series of these directed paths chains, which are formed by just taking the matching from the smaller side to the larger side. You can kind of stick them together. So you can decompose the Boolean hypercube into these vertex disjoint paths. The Lehman-Ron theorem can be thought of in that vein. So what it says is consider two level sets. So you have these two level sets, which are basically like all the vertices of the same Hamming weight. So we'll consider two sub-level sets, S and T. So that means that S and T are contained in level sets. So all the vertices in S have the same Hamming weight. All the vertices in T have the same Hamming weight. And we'll have what is called an ordered bijection, denoted by phi, between them. So what this simply means is that this is a bijection according to the partial order. So we have a bijection phi between S and T, such that for every little s, every element in S, phi of little s is actually greater than S according to the partial order. The Lehman-Ron theorem makes this rather remarkable, proves this remarkable statement. It says that if you have S and T such that they have this ordered bijection between them, this bijection according to the partial order, then there actually exists S vertex disjoint paths from S to T, which means you can basically match everyone in S to someone in T by a vertex disjoint path. Just as a comment, this matching that you get according to these vertex disjoint paths is not the same as the matching phi. So this is the Lehman-Ron theorem. It's just a fundamental theorem about the Boolean hypercube. Uh, and so let me sort of tell you why it's a remarkable statement. So we want to route from S to T in vertex disjoint paths, according to the directed Boolean hypercube. So as I said, it's a regular bipartite graph between two layers. And so we know that, there's a perfect matching from S to some subset of the next level. But observe that there could be many potential sets in the next level. That's the yellow set that S could match to. So it could match to this other potential set, or maybe this other one, so on and so forth. And what the Lehman-Ron theorem says is that we can actually choose these in such a way and chain those matchings together to get vertex disjoint paths all the way from S to T, which is quite remarkable that as long as T has this sort of comparison bijection, this precedence bijection according to phi, then one can always chain these matchings in such a way that you can get from S to T in vertex disjoint paths. And so again, I present the Lehman-Ron theorem to you. So consider S and T, these level subsets with this bijection according to the ordering, that's phi. There exists capital S, the size of S, vertex disjoint paths from S to T. The starting point for our result is actually a new proof. So I'm going to take a few slides just to explain this new proof. Then I'll tell you what we actually prove and why this is sort of connected to deeper questions in monotonicity testing. So let's start with a minimal counterexample to the Lehman-Ron theorem. So what this means is, by the Max-Loh-Minkah theorem or Menger's theorem, because this is a minimal counterexample, the amount of the number of vertex disjoint paths between S and T is exactly S minus 1. And so if you look at the ST cut in the directed graph, the size is S minus 1, where S, the cardinality of S minus 1. By duality and complementary slackness, so not only do we have a bound on the cut, what we know is there exists cardinality of S minus 1 vertex disjoint paths from S to T saturating C. Okay, so that was a lot of words. I'll show you in a picture. We'll call this capital pi. It basically means that we can find the cardinality of S minus 1 paths, which are vertex disjoint, that go from S to T, such that each path contains exactly one cut element. So you see those red vertices are the cut elements, and we have these paths. So these paths are special. They pass through the cut exactly once. They start at the S side, they go through a cut vertex, then they go to the T side. And so the S side of the cut is like on this yellow part, this yellow amoeba that I've drawn over there, is everything on the S side, which is bordered by the cut capital C, and then you have the T side. And what we know is that there is a single little s in the set capital S that does not participate in these paths. Why? Because we have cardinality of S minus 1 paths. And of course, so there's one little s, that doesn't participate in the path. Our plan is to engineer a contradiction as follows. So let's focus on the graph that is formed by the union of all of these ST paths. Any path that goes from capital S to capital T. So not just the ones that are drawn, but any path. So just take the graph G that is the union of all of those paths. And again, I'm talking about directed paths here. The little s is on the capital S side, and it's not on the paths. I'm going to discover another vertex that I call x1, which is also going to be on the S side and not on the paths. And from there, I'm going to find an x2, which is on the next level, which is on the S side and not on these paths. And so on and so forth. Eventually, I'm going to get all the way to that last level before T, find this xk, which is also going to be on the S side and not on these paths. And this is a contradiction because this lies in this graph that is, contains all ST paths. So this xk has an edge into T. And so we have a path from S to T that doesn't go through any cut element, because remember, all the cut elements were on those paths capital Pi. And this would give a contradiction. Now, I'm going to give you sort of a one-slide proof or little summary of the idea of just how do you proceed one step of this argument. So remember, we have this little s, and we took this graph that consists of all these paths, st. So this little s has some edge that goes to the next level. That's marked in this purple dashed line. Now, if the other endpoint of that edge did not lie on these paths, then we're done, because obviously it's on the s side, because it's connected to some vertex, it's connected to little s, and it doesn't lie on the path, so we'd be done. So victory. And so instead what happens is that when you take some edge, it bumps into the path. And so what did the adversary tell S at this point? It said, despair will lead you nowhere. Okay, let's go back and look at this edge. So let's just say this is an I-dimensional projection in the Boolean hypercube, right? So from S, you took this projection and you ended up on the path. This is an I-dimensional projection. Let me go ahead and look at that blue edge, which is just along the path. And let me project down from the other endpoint of the blue edge. So as you see in the picture. Now this dotted blue line is actually just a projection, the I-dimensional projection of the blue edge. Now, if that vertex that we discovered was not on the paths pi, on the black part, well, then we're already done. So victory. So what must happen is that when you project down, you must end back on the path, on a different path. And so what we'll do is play this game again. So we'll follow this blue edge, just go back into capital S, and we'll project up again. And so now we can project up from there along these I-dimensionals. So if you look at this carefully, you'll see that every time the dotted line goes up, I'm incrementing the I-dimensional, the I-coordinate, and the dotted line comes down, I'm decrementing the I-coordinate. And so I project up again, and maybe I end up on this path again. And then I follow the blue edge on the path, I project down, and I try to I keep doing this process. So we're always taking matchings, if you think about it. The I-dimensional projection is a matching, and these blue edges, which are along the path, are also matchings. So we start from S, we'll never see it again. And so this process has to complete somewhere. And when you complete this process, we will discover something in that next level, which is on the S side of the cut, but not on the paths. And we would have to repeat this argument level by level, and that becomes a little more complicated, but that's the basic idea. And so this is how we get a contradiction, and we would prove the Lehman-Ron theorem. Our result actually is you take that idea, and if you work with that idea, you can prove something stronger. So let's take S, T, and phi just as before. Now assume that S and T are distance r greater than 1 apart. So they're at least distance 2 or more. And let me say an LR solution is a set of cardinality S vertex disjoint paths. So the LR theorem says there exists an LR solution. What we can prove is actually there exist at least 2 edge disjoint LR solutions. So remember, LR solutions are cardinality of S vertex disjoint paths. And we can actually find 2 edge disjoint copies of this. And we have a general conjecture which says that if these were distance r apart, there exist r edge disjoint LR solutions. So the further apart they are, the more edge disjoint LR solutions we can find. We were only able to prove it for r is equal to 2. And there's actually a statement in terms of routing. So if you take the Boolean hypercube, you set the edge capacity to be 1 and the vertex capacity to be r. That's the amount of flow that can go through a vertex. then this conjecture that we stated basically says that R times S units of ST flow can be routed. And the conjecture is equivalent to the one that I stated before. At this point, you might ask why. Why are we studying these questions? And it connects to one of the most basic problems in property testing, that of monotonicity testing. So the seminal result of Goldreich, Kohlwasser, Lehman-Ron, and Samorodnitsky says, suppose you consider a Boolean function on this hypercube, which is basically this directed hypercube. A function is monotone if for all x less than y, f of x is at most f of y. So the way to think of a monotone function is it's an indicator of a monotone set. And I've shown that, in that orange part over there, a cartoon of a monotone set. So the aim is given an epsilon, which is a proximity parameter. We want to distinguish a monotone function, which is the distance to monotonicity being 0, versus a function that is far from monotone. And I won't get into the specific details of this problem. That is not as important. And so one of the major questions asked was, what is the non-adaptive complexity of monotonicity testing? It turns out that these routing questions that I talked about are intimately connected with this question. So if you look at the history of monotonicity testing, the first GGLRS paper gave a tester with complexity D, which is the dimension. And the core proof basically is about 2 pages long. That bound stood for more than a decade until it was improved to d to the 5/6. And that was about 8 pages long. And it was actually quite, at that point, a surprise that one could even beat this d bound. And then a seminal result of Koht, Minzer, and Safra got down the tester complexity to square root d, which is the optimal bound, up to some log factors. And their core proof is about 30 pages long. These statements turned out to be connected to something known as directed isoperimetric theorems. And a directed isoperimetric theorem is some kind of measure of a directed surface area. And I've stated Poincare, Margulis, and Talleyrand, which are progressively more and more difficult directed isoperimetric theorems, all of which are connected to improvements in the tester query complexity. So the Lehman-Ron theorem, the LR theorem, was central to actually proving the directed Margulis theorem. And it was the first step towards little o of d testers whose query complexity is smaller than the dimension. And the directed Margulis theorem has elegant is maybe in the eye of the beholder, but it has a nice combinatorial proof. The Koht-Minzer-Safra theorem is more analytic, it's much more involved. And one of the questions behind all of our work is, could we prove generalizations of routing statements that could prove the directed Talleyrand theorem? And indeed, what we discovered is that there is a flow connection. So every directed isoperimetric theorem is equivalent to a directed hypercube routing theorem. The Poincare statement is only about having edge capacities. The Margulis statement is a stronger version of Poincare plus a statement about vertex capacities. And the Talleyrand statement appears to be equivalent to having simultaneous edge and vertex capacities. And I say appears because I'll qualify that in just a moment. So let me now just take a last couple of minutes to show you this connection using some pictures. So what is known in the literature of monotonicity testing is that if your f is epsilon far from monotone or constant far from monotone, there exist large sets S and T, where S has value 1, T has value 0, and these are large, meaning that they're like a constant fraction of the Boolean hypercube, such that there exists, again, a precedence matching or an ordered matching between S and T. So if you remember the Lehman-Ron setting, we also had an S and T, except S and T were level sets or level subsets. They were contained in levels. In this case, they're not necessarily contained in levels, so they could be spread out. But between S and T, you have this matching according to phi, which is an ordered matching. So for every little s, it's matched to a little t, such that little s is less than little t according to the partial order. The directed Poincare statement is equivalent to the following. Given S and T and edge capacity is 1, you can route cardinality of S units of flow. This is different from Lehman-Ron. In the Lehman-Ron theorem, they had to be vertex disjoint paths, and here they only have to be edge disjoint. The directed Margulis statement is a little more sophisticated. What it says is, so you have these S and T's that are matched. Consider the S and T with the minimum average distance. So kind of push them, so maintaining their cardinality, kind of push them close to each other and get the minimum average distance between S and T. Then it has been shown that if the edge capacities are 1, you can route R times S units of flow. So this is stronger than Poincare because you can do R times S, cardinality of S. And using the Lehman-Ron theorem, you can show that if the vertex capacities are 1, you can send cardinality of S divided by R units of flow. So there is a multiplication by R and division by R. And actually, when you multiply these together, they cancel out, which leads to the Margulis theorem. So what this says is there are basically two statements. There is a vertex routing statement based on the LR theorem, an edge routing statement, and combined together, they actually give the Margulis theorem, which is a more sophisticated statement on the directed boundary. The following statement I'm giving actually implies the directed Talleyrand theorem. So again, take the minimum average distance. So find S and T, which minimize their average distance. Set the edge capacities to be 1 and the vertex capacities to be R squared, where R was that distance. We conjecture that you can send R times S units of flow. So this is a simultaneous edge and vertex constraint capacity. This statement implies the directed Talleyrand theorem. And so we believed that the generalized Lehman-Ron theorem could prove that routing statement. So there are connections between the generalized Lehman-Ron theorem and the routing statement. We thought we could prove it. We couldn't. We thought we could prove the generalized Lehman-Ron theorem. We couldn't do that either. And we could only prove it for R is equal to 2. One of the reasons to look into this is that the Lehman-Ron statements generalize to more richer product structures, which are hypergrids, than just the directed Talleyrand approaches of Koopmans and Safra. I leave you with this conjecture. It's just a combinatorial conjecture about routing in the hypercube. So you have S and T being sub-level sets. They are distance R apart. The edge capacity is 1. The vertex capacity is R. Prove that you can route R times cardinality of S units of flow from capital S to capital T. I leave you with the last slide. And here's a link to the archive version of our paper if you're more interested.